to this course. First of all, let me thank the SIMPA and ICTP organizers for providing the chance of my visit, and also for this course. And also I have thanked the Institute for Logic, Language and Computation, where I'm visiting there. And also I have thanked Nick Bijanishvili, who is my host in ILC. Okay, I'm going to talk about topological semantics of modal logic. I'm going to consider no specific preliminaries for this course, but familiarity with basic notions of topology and also classical logic would be great. Okay. Let's see. Modal logic is a subfield of mathematical logic that consider a formal study of qualifying the truth of judgment, including modal expressions such as necessity, belief, obligation, and knowledge, time, and so on. Formally, modal logic is a classical logic which we added to it a modal operator. Because in classical logic, we can't formulate sentences which contains a modal operator, modal expression. So we have to add another operator to classical logic to be able to formulate these kinds of sentences. We have one modal operator, box, or its dual, which is shown by diamond. Since they are dual of each other, we can say that we add diamond to the classical logic, or we can say that we add box to the classical logic. The term modal can also be used to model many other modes of truth, and by interpreting box as other modes of truth, we can have other kinds of logic, such as epistemic logic, where box is interpreted as phi is known by the agent, or temporal logic, where box is interpreted as phi will be always true, dynamic logic, or so on. As we see, modal logic is expressive, but it's a fragment of first order logic. But its advantages with respect, its advantages comparing with first order logic is that it's decidable. We won't talk about decidability during this course, but I just want to mention that modal logic is a decidable fragment of first order logic, and it has very good expressive power. Different semantics have been introduced for modal logic, such as algebraic semantic, topological semantic, cryptic semantics, or neighborhood semantics. Topological semantics of modal logic was introduced by McKinsey and Tarski in 1930s and 1940s. After that, relational semantic was introduced by Kripke in 1960s, when he was very young, I think maybe around 18 years old. And I have to mention that Zoghifard passed away in a few months ago. After proposing relational semantics, since he's very easier to work with them, it's kinds of graph. I will introduce it a little bit later, because it has a very easier structure, and it's very easy to work with them. After introducing this semantics, topological semantics went in the shadow. But nowadays, because of its mathematical interest, and also because topological structures found many application in other areas such as computer science, topological semantics draw more attention nowadays. And during this course, I will talk about this. And also, the other point is that after, by using the relational semantics, by using the method and results in cryptic semantics, they found some other ways to prove something in topological semantics. And it makes it easier to prove something in topological semantics too. Because of that, I start the course by introducing cryptic semantics. After that, I will talk about topological semantics. There are two kinds of topological semantics that introduced by McKinsey and Tarski. In one, the modal operator diamond is interpreted as the closure operator, and in the other, the modal operator diamond is interpreted as a counter-derived-set operator. We will talk about them in details in the next sessions. And if time permits, we will talk about probability logic, the topological semantics of probability logic, which is one of the interesting branch of modal logic. In probability logic, the modal operator box is interpreted as box phi is interpreted as phi is provable in some formal systems. We will talk about them in the maybe last session. Okay, these are the main literature that I will use for this course. I'll try to mention the other references during the course or maybe at the end of the course. Okay, let's start the formal definitions. Modal language contains a set of propositional letters which we denote it by a prop, and each proposition we show it by P, Q, R, and so on. As I said, in modal logic, we add a modal operator box or diamond to the classical logic. The formulas of modal logic is defined by this grammar. Each propositional variable is a formula. This notion is called falsumo, but it's a formula which is always false. If phi is a formula, then the negation of phi is a formula. If phi and psi is a formula, the disjunction is a formula. Also, if phi is a formula, then diamond of phi is a formula. One thing that I forgot to mention at the beginning is that because I don't have any information about the background of the participants, I'm going to use both the slides and board. In this way, I can talk about the basic definitions on the slides, and we can talk about the details on the board. If you have any question and if I'm going too fast or too slow, please let me know. In this way, I think we can manage the time better. So please let me know. And also, after stopping the recording, you can ask your questions and we can discuss about the course. Okay, let's continue. Okay, as I said, we have these kinds of formula. Also, we can define, for example, the conjunction by using the negation and disjunction. The conjunction of bias and psi is defined as the negation of the disjunction of their negation. Also, for the arrow, sure. Yeah, it's better. Yeah. Okay. Also for arrow or left right arrow, you can use negation and disjunction. As I said, we can define the dual operator for diamond, which we show it by box, and box phi is the negation of the diamond of the negation of phi. Usually diamond is box is interpreted as it's necessary, and diamond is interpreted as it's possible. And as I said, there are different interpretation for them, which makes different logics. Also, we can have more modal operator with different arity, but because we want to make the definitions and notions easier, we just consider the one unary modal operator during this course. Okay, now I'm going to talk about Kripke semantics. A Kripke frame is a pair W and R, where W is a non-empty set, which is a set of possible words, and R is a subset of W times W, which means that R is a binary relation on W. But in this way, I have to. A Kripke model is a triple W, R, and V, where W and R is a Kripke frame, and V is evaluation function, which is a function which assigns to each propositional variable a subset of W. We can see a Kripke model as a graph. For example, we can have this kinds of a structure. For example, W1, W2, W3, W4, or I don't know, something like that. We can see it as a Kripke frame. And when we want to have a Kripke model, we should mention that which proposition is true in each word. For example, we have P true in here, Q and P and Q is true in here, Q is true in here, and for example, none of P or Q is true in here. It's a Kripke model. So as you can see that Kripke models is like a graph, and we have just mentioned that which proposition is true in each word. Then, okay. Suppose that W is a point in a model. The notion of a formula being satisfied in M is defined by induction. For example, P is true in W if and only if W is in V of P. A false loop is true nowhere. The negation of phi is true in W if and only if phi is not true in W. The disjunction of two formulas is true in W if at least one of them is true in W. Diamond of phi is true in W if and only if there is at least one successor of W where phi is true. So if we want to have diamond of phi true at W, there should be V in W, which is accessible from W by R, and phi is true in V. Box of phi is true in W if and only if for all successors of W, phi is true in them. So for example, in this model, we can see that W2 satisfies P, or W2 satisfies P and Q, or for example, W1 satisfies the negation of Q because Q is not true in here. For diamond, for example, we can see that W2 satisfies diamond of Q because W3 is accessible from W2. We have W2 or W3, and W3 satisfies Q. So diamond of Q is true in W2. And W2, we can see that does not satisfy box of Q. Why? Because if we want to have box of Q true at W, all successors of W should satisfy Q. But W4 is a successor of W2, and Q is not true in W4, so box of Q is not true at W2. Is it clear? If you have any question, you can write it in the chat and I will read it. If it's not clear, I can provide some more examples. Okay. No question. We say that a formula phi is satisfiable in M if there is a point W such that phi is true at W. For example, I can say that P is satisfiable in this model, or the amount of Q is satisfiable in here because there's a point W2 where the amount of Q is true in here. A formula phi is valid in M if it's true at all points of M. And we can define these notions for a set of formula. For example, a set of formula is true at W if all members of this set is true at W. Also, we can talk about the validity of formula in a frame. A formula phi is valid in a frame F, and we denote it by this notion. If it's true, phi is true in any model based on F at any point. So phi is valid in F if for any model M based on F and any point W in W, we have that phi is true at W. A formula phi is valid on a class of frame if it's valid on every frame in K. And also we say that a formula phi is valid if it's valid on the class of all frames. Again, we can extend these notions to a set of formula. We say that a set of formula gamma is valid on a frame F if every members of gamma is valid on F. Let's see some example. For example, I want to show that this formula is a valid formula. So I'm going to show that the amount of P or Q, then the amount of P or the amount of Q is a valid formula. To show that, I have to show that for any given frame F, arbitrary frame F, and any model based on F, which is F and V, and for any given W in F, M and W satisfies the amount of P or Q, then diamond of P or diamond of Q. So since we have an arrow in here, we have to assume that M and W satisfies diamond of P or Q, and we have to show that in this case M and W satisfies diamond of P or diamond of Q. So if we have this means that there exists W prime, which is accessible from W, and in W prime, P or Q is true. So by definition of satisfaction, we know that this means that M and W prime satisfies P, or M and W prime satisfies Q. So there exists a point W prime accessible from W where P is true or Q is true. So this means that M and there is a point W prime. W prime is accessible from W. If P is true in W prime, then diamond of P is true at W. If Q is true at W prime, then diamond of Q is true at W. So M and W satisfies diamond of P, or M and W satisfies diamond of Q. So we have our point. Diamond of P or diamond of Q is true in W. Since F, M, and W, all of them are arbitrary, then we can say that this formula is a valid formula. Okay. Let's see another example. It's better the other one. Yeah. Sweat. Yeah, thank you. Yes. I want to show first that this formula is not a valid formula. So what does it mean that this formula is not valid? It means that there exists at least one frame, and to show that it's not valid, I have to show that there exists at least one frame F and one model M based on F, and a point W in F such that in M and W this formula is not true. So to show that, it suffices to provide a counterexample. Consider this simple model. We have W1, W2. Then we can see that W1 satisfies P, but P, then diamond of P is not true in W1 because the only possible accessible word from W1 is W2, and P is not true in W2. So this formula is not true in W1. This means that this formula is not a valid formula. But we can say something more about this formula. we can show that this formula is valid on the class of reflexive frames. It means that for any frame f, if f is reflexive, then this formula is valid on f. So to show that, assume that given a frame f, which is reflexive, and M is any model based on F, and W is any point in F. So it's very simple, and you can see it very easily. If N and M and W satisfies P, since W is accessible from itself, it means that M and W satisfies diamond of P because we have W or W. So it means that M and W satisfies P, then diamond of P. So for any given reflexive frame F, this formula is valid on this frame. As an exercise, you can show that this formula, diamond of P, then diamond of P, is valid on the class of transitive frames. You can try to prove it, and if you have any problem, we can discuss about it after this, at the end of the course, or maybe tomorrow. Okay. Strong. Oh, okay. In mathematics, maybe in other branch of mathematics, we usually want to know when two different structures have the same behavior. For example, when two topological spaces are homeomorphic or two algebraic structures are isomorphic. In here, we want to know when two cryptic models have the same behavior, which means that when they satisfy the same formula. This notion by simulation provide the tools that we can check that when 2 points in different models have the same behavior or not. Okay. Suppose that we have two models M and M prime. A non-empty binary relation Z is called a bisimulation between M and M prime if the following conditions are satisfied. Let me put it in here. First, W and W prime, if they are related by Z, then they have to satisfy the same propositional variables, which means that if W is in V of P, then W prime should be in V of P. The other condition says that if W and W prime are related by Z and V is accessible from W in M, then there should be a V prime in M prime, which is accessible from W prime, and V and V prime are related by Z. This condition is called as a fourth condition. We have the converse of this condition, which called as a back condition. Maybe it's better to show these conditions on picture. For example, it's a model M and it's a model M prime. It's a point W in here. We have W prime in here. Where's the color? And this is a relation Z, which related these points. The first condition says that if P is true in here, then P should be true in here and vice versa, which means that if W is in V of P, then W prime should be in V of V prime of P and vice versa. The fourth condition says that if W is related to some point V in M, then in M prime, there should be another point V prime, which is accessible from W prime. And these points are also related by the bisimulation relation. So it's the fourth condition. The back condition says that in this direction, if V prime is accessible from W prime in M prime, then there should be a point V in M, which is accessible from W, and they are related by bisimulation relation. If W and W prime are bisimilar, we say that they are bisimilar if there is a bisimulation which related these 2 points. Let's see some example. I think I have in here. As a simple example, for example, M is a model which has just one reflexive point, and M prime is a model which has 2 points, for example, W1 prime and W2 prime. I can define a bisimulation between these 2 models. It just suffices to connect this point to both of these points. I mean that our relation is that W and W1 prime and W and W2 prime. There is no valuation true in any of both, so the first condition is true. If P is true in here, I should have P in these 2 points too. And in M, we have W accessible from W, and since W is related to, for example, we have W set W1 prime. In here, I have W, which is related to W again. In here, I have W1 prime, which is related to W2 prime, and there is a Z between these 2 points. So the fourth condition is true. Again, we can check that the back condition is true in here too. It's one of the simple examples that we can see. Or suppose the other example, for example, So I want to define a bisimulation between these two structures. How can I do that? You can see that because in here I have some points which are dead end point, which means that they don't have any successor. So I can't connect these points to this point because it has some successor. But I can connect these points to this one because it's dead end point 2. And for the other points, I have to connect them to these points. So it's a bisimulation between these two models. I'm not sure that if you can consider the other color in here. I'm not clear in the photo. Maybe I have to use the other. Yeah. Let's show them by the other color. Yeah. Yeah. It's a bisimulation between these two structures. As I said, we're going to use this notion to check where two models have the same behaviors, which means that they satisfy the same formula. By simulation, we can have this theorem, which says that modal formulas are invariant under bisimulation, which means that if 2 points W and W prime are bisimilar, then this notion is used as an equivalent. They are equivalent, which means that they satisfy the same formulas. We can prove this theorem by induction. It's very easy, but just talk a little bit about that. If W is related by W prime by simulation, I want to show that for any given formula phi is true in W if and only phi is true in W prime. By induction formula, I mean that we have to consider the base case, which phi is a propositional variable. Then if W satisfies P, which means that W is in V of P. By the first condition of by simulation, we know that W is in V of P if and only if W prime is in V prime of P, which means that W prime satisfies P. The other condition is that for the negation of psi, assume that this claim is true for psi. We want to show that it's true for the negation of psi. It's easy. If the negation of psi is true in W, then it means that psi is not true in W. And by induction hypothesis, it means that psi is not true in W prime. So it means that W prime satisfies the negation of psi. The other cases for example, psi 1 or psi 2, it's easy to check that. The key cases for the modal case when phi is diamond of psi if W satisfies the amount of psi, then it means that there is a point W prime which is accessible from V accessible from W, and in V psi is true. Now by the fourth condition, we know that there is V prime which is accessible from W prime in model M prime, and V is bisimilar to V prime. So V is bisimilar by V prime and psi is true in V. So by induction hypothesis, we can see that psi is true in V prime and V prime is accessible from W prime. So W prime satisfies the amount of psi. For the other direction, I mean that to show that if W prime satisfies the amount of psi, then the amount of psi is true at W, we have to use the back condition. So by the fourth and back condition, we can see that W and W prime satisfy the same formula. Note that the converse of this theorem is not true, which means that if W and W prime are 2 points in different models which are modally equivalent, we can be sure that there is a bisimulation between these two models. Let's see by an example. Suppose that M is this model. And M and M prime are two models. In each of them, we have for any natural number n, we have a branch of length n in each of these models. The difference between these two models is that in addition of these branches, we have a branch of infinite length in M prime. So one can show that these models, these points W and W prime, are equivalent in these two models, but we can check that there is no bisimulation between these two models. Sometimes for bisimulation we use this notion, but yeah. Because if you start to go in this branch, you can't find any appropriate successor in W for going through that and to match the back and forth between these two models. So the converse of the bisimulation invariance theorem is not true in general. To have the converse of this theorem, we have to extend our language with infinite conjunction or disjunction, or we have to restrict the class of models. One of these classes is the class of image finite models. A cryptic model M is image finite if for each state W, the set of its successor is finite. By RW, I mean the set of successors of W. We call these kinds of model the image finite model. Then there is a theorem by Hennessy and Milner which shows that if M and M prime are two image finite models, then for every point W and W prime, we have that W and W prime are bisimilar if and only if they are modally equivalent. Because of the time, we can't prove this theorem, but if you are interested to see the proof, you can find its proof in the first references I mentioned in the beginning of the course. Let's start the second part of this session. As you saw, the cryptic models are relational models. We have a relation over some set. And as you know, we can talk about relational structures in first order logic too. If we have, I want to mention that if we have a appropriate language, we can define a translation from modal language to first order language. To see this, first consider first order language L1, which contains the equality symbol, a binary predicate R, and also for each proposition P, a unary predicate. Consider this language. Then any cryptic model also can be seen as a model in this language, as a first order model for this language, because we have a set, non-empty set, which is a domain. We have an accessibility relation, which we can consider as an interpretation for R, and V is a valuation function from the set of propositional variables to power set of W, which we can consider it as an interpretation for each predicate. Now we can define a standard translation. Let X be a first order variable. The standard translation of modal formula is defined as follows. The standard translation of a proposition P is P of X, where P is a predicate that we assign to P. The standard translation of falsum is any formula which is always false, such as X is not equal to X. The standard translation of negation of phi is the negation of a standard translation of phi. The standard translation of phi or psi is the disjunction of the standard translation of phi and a standard translation of psi. And the standard translation of diamond phi is there exists some y where y is related to x, and a standard translation of phi. As you can see, and the standard translation is a reformulation of the satisfaction relation, because we said that in the point W, diamond of phi is true if and only if there is some point P where P is related to W and in V phi is true. And it's exactly the reformulation of this property. And in here, here y is a variable which it's a new variable and it's not used before that. So you can see that the standard translation of box phi is for all y or xy, then a standard translation of phi. Let's see an example. For example, I want to define the standard translation of diamond of x of p, then q. Okay, we have diamond in here, so it's equal to say that there exists y1 r xy1 and sty1 of xp, then q. The free variable x or y in here, y here, or when we define standard translation, the free variable is used to show the current state. Now we have again the exist y1, rxy1, and sty1 of xp, then sty1 of q, yeah, which is the exist y1, rxy1, and for box we have that for all y2 if r1, ry1, y2, then sty2 of p, then, and the standard translation of q is qy1, where q is the predicate that we assign to q. Then we have exist y1, rxy1, and for all y2, ry1, y2, then p of y2, then q of y1. And p is a predicate that we assign to p. Then by induction on the complexity of modal formula, we can show that for any formula, modal formula phi, if phi is true in point w when we see m as a Kripke model, then the standard translation of phi is true in m when we see m as a first order model, and by assigning w to the free variable x. It's a typo here. In some literature, they use this notion to show the satisfaction in modal logic, but in some other, and also I use this notion, and here is a typo. By the way, this proposition provides a bridge between first order logic and modal logic. And we can prove some properties from one to other by this proposition. For example, we know that first order logic has the compactness property, which means that for any set of formulas, if its finite is satisfiable, then it's satisfiable. We know that first order logic has the compactness property. By this proposition, we can show that modal logic has the compactness property too. So we show that for any modal formula, there is a corresponding first order formula. So one may ask if the converse of that is true, which means that for any first order formula in the language L1, there is a modal formula, which this first order formula is equivalent to the standard translation of that modal formula. The answer is no. Just by considering the syntax, you can see that it's not true for our formula. Also, we can show that for simple formula, this is not the case. For example, consider the formula Rxx. It's a first order formula in the language L1. And assume that it's equivalent to a standard translation of some modal formula. But we know that modal formula are invariant under bisimulation. So if M and W is bisimilar to N and V, then phi is true in W if and only phi is true in V. Now consider M as this model and N as this one. We know that W and V are bisimilar. We can define bisimilation between these 2 points. So if phi is true in here, then phi should be true in here. And we know that RXX, RWW is true in here. So if phi is the standard, if RXX is equivalent to the standard translation of phi should be true in here. So phi should be true in here. And again, RVV should be true. And we know that it's not true here. So RXX cannot be equivalent to the standard translation of some modal formula. And bisimulation is a tool that we can use to show that this formula is not equivalent to translation of some formula. It's exactly what Van Bentham proved. There is an interesting and important proof, theorem, which proved by Johann van Bentham, which shows that any first order formula with just one free variable x is equivalent to a standard translation of a modal formula if and only if it's invariant under bisimulation. So by this theorem, we understand that modal logic is a fragment of first order logic which is invariant under bisimulation. Okay. Until now, I've talked about cryptic models, their relation with each other, and some properties about that. Now let's talk about cryptic frames and definability, the level of frames. What I mean by definability. Recall that we said that a formula phi is valid on the frame F if and only for any model M based on F, and for any point W in W, phi is true in W. Now we say that a formula phi is formula phi defines a class of frame K if for any frame F we have that F is in K if and only phi is valid on F. Similarly, we can say that a set of modal formula gamma defines a class of frame K if and only for any frame F we have that F is in K if and only if gamma is valid on F. And a class of frames is definable if there is some set of modal formulas that defines it. Let's see some example. We want to show that the formula P then diamond P defines the class of reflexive frames. Before we showed that if our frame is reflexive, then this formula is valid. Now I have to show that if this formula is valid on some frame, then this frame is reflexive. Okay. So to show that P then diamond P defines a class of reflexive frames, we have to show that if our frame is reflexive, then this formula is valid. This we show that it in the previous part. And also we have to show that if this formula is valid on some frame, then this frame is reflexive. And I want to show that by contraposition. Suppose that F is not reflexive. So it means that there is some point in F which is not related to itself. It means that W and W is not in R. So we have a point W, it may have some successor, but we know that W is not related to itself. Now consider for evaluation P, which assigns P to W and no where except W. Then W satisfies P, but W does not satisfy diamond of P. So P then diamond of P is not true in this model if we have a M equal to F and V is this valuation. Then in M and W this formula is not true. So this formula is not valid on F. So if our frame is not reflexive, this formula is not valid, which is equivalent to say that if this formula is valid, then our frame is reflexive. Again, as an exercise, you can try to show that the formula diamond P, then diamond P defines the class of transitive frames. So each of these properties, reflexivity and transitivity, are definable in first-order logic too. For example, reflexivity is definable by the formula Rxx, transitivity by Rxy, and Ryz, then Rxz, for example. So these are the properties which are definable in first-order logic and also in modal logic. But we can provide some examples which shows that there are some properties which are definable in first-order logic but not in modal logic, or there are some properties which are definable in modal logic but not in first-order logic. Another point that you have mentioned that this example shows that there is the difference between the level of models and frames. When we work with frame, the reflexivity is definable by this formula, and as we saw, reflexivity is not definable when we work in the level of model. Let's see another example. The Lob formula, which is an important formula and used to the probability logic. And if time permits, we will talk about probability logic at the end of this course. And we saw this formula there. The Lob formula defines the class of frames where R is transitive and the converse of R is well-founded. Well-foundedness is the property which says that R is well-founded if there is no infinite sequence ending to some point. There's no infinite sequence like this. So the converse of R is well-founded if there is no infinite path starting from some point. So in particular, we don't have any cycle or loop. We don't have enough time to prove that, but if time permits, we will prove that in the last session. But you can see that the converse well-foundedness is a property which is not definable in first order logic. So Lob formula characterizes a class of reflexive and conversely well founded, but this class is not definable in first order logic. So we can see that modal logic provides a good expressive power. So we saw an example which is modally definable, but it's not first order definable. Now I want to mention some construction which help us to see when a property is modally definable or not. The first one is disjoint union. Disjoint union is defined very easily when we have two or more disjoint frames. Their disjoint union is defined by putting them together. The W is the set of the union of all Wi, and R is the union of all Ri. Then we can prove that for any modal formula phi is valid on the disjoint union of fi if and only phi is valid on every of fi. So for any class of frames which is modally definable, this class should be preserved, should be closed under disjoint union. Also, we can use this property to show that, for example, some property is not modally definable. For example, the class of finite frame is not modally definable, but because you can consider an infinite singleton frames. For example, it's a frame F1, it's frame F2, and so on. When you consider infinitely many such frames, their disjoint union is not finite, but each of them is finite. So finiteness is not definable in here. The other property, the other construction is generated subframe. The frame F prime is a generated subframe of F if F prime is a subframe of F, which means that W prime is a subset of W and R prime is the restriction of R to W prime. And if we want to have the generated subframe, we have to have this property too, which says that for any x in W prime, if y is accessible from x, then y should be in W prime. We can see, for example, it's in the picture. For example, it's W1, W2. Something like that. Then when I want to consider this, it's a subframe of our first frame, but it's not a generated subframe. If it wants to be a generated subframe, since W3 is related to W4, we have to have W4 in here. So for example, we can, if we want to have generated subframe, we have to have this point too. Yeah. Or we can define the generated subframe from W3, which is this frame. It's a frame generated by W3. Again, we can show that if F prime is a generated subframe of F, if phi is valid on F, then phi is valid on F prime. So again, by this theorem, we can show that, for example, some properties are not modally definable. For example, this property which says that there exists one point which is reflexive. So, for example, if this formula is true in here, or maybe it's better to consider this frame. Oh, sorry. For example, this frame. We have this frame. When I want to consider the generated subframe of W grid, it's just a singleton, which is not related to itself. So this formula is not true in here, but it's true in here. So we can use the generated subframe to show that some properties are not modally definable. The other construction is a bounded morphism. A bounded morphism is a function between two frames, between their the set of their states, which says that if W is related to V, then f of W should be related to f of V. And the back condition says that if we have that fw r prime v prime, then there exists V in the model M, which is related to W, and f of V is V prime. We say that f prime is a bounded morphic image of f if f is an unto bounded morphism. Again, we can show that if f prime is a bounded morphic image of f, then phi is valid on f if and only phi is valid on f prime. For example, you can see an example of bounded morphism. Suppose that we have frame n, which is 0, 1, 2, 3, and so on. And I have a frame in this form. Then I can define a bounded morphism from its model M, and it's a model M prime, from W to W prime by saying that f of n is E if n is an even number, and O if n is an odd number. Then f is a bounded morphism. Again, we can use this construction to show that some properties is not modally definable. For example, the property of for all x, the negation of r x x. We can define a bounded morphism between this frame again and just this frame. I can send any point to this single point. Then it's a bounded morphism. In here, this formula is true, but in here this formula is true, but not in here. So this property is not modally definable. All of these properties can define also on the models by adding the condition that 2 points with that the condition for the evaluation function. For example, in here we should add that if that p is true in W, then p is true in f of W. Then we can see that all of these properties are a special case of bisimulation. Okay. There is a theorem which proved by Godel-Lob and Thomason, and says that these constructions are necessary to see when a class of frames is definable. It mentions that if K is a class of frame which is first order definable, then its model definable if and only if it goes under bounded morphic images, generated subframes, disjoint unions, and reflex orthofilter extensions. Orthofilter extensions is another construction which, because of the limitation of time, I didn't talk about it, and yeah, we can talk about it because it needs more to say about that. Yeah, but it's a very important theorem in the model theory of modal logic. Okay. Okay. Another property of modal logic is that any satisfiable modal formula is satisfiable in a root of the root of a tree. By tree, right now, just consider its definition in graph theory. We will talk about trees in the next sessions in a more detail, but right now, just consider its definition in graph theory. I want to show that for any formula phi, if phi is satisfiable, then it's satisfiable at the root of a tree. Okay. To show that, suppose that M and W satisfies phi. Without loss of generality, by generated subframe, we know that we can consider that M is generated by W. Now, let W prime be the set of all finite sequence of this form. For example, W U1 to UN, where we have this property. Consider this set of states. I have to define a relation between these states. We say that W U1 to UN is related to W B1 to Bm if and only if M is equal to N plus 1, and for any I less than N, Ui is equal to Vi. And we have that Vn are Vn plus 1. Also for valuation, we say that W and U1 to UN is in V prime of P if and only if UN is in V prime of P. Then we have a model M prime, W prime, R prime, and V prime, and I can define a function f from W to W prime, which distance any point U to the sequence which ends in U. Oh, sorry, from W prime to W. Have to define f from W prime to W. I send any sequence to the last point. Then you can see that This function is a bounded morphism between these two models. This method is called unraveling. So by this method, I can show that any satisfiable formula is satisfiable at the root of 3. Okay. Uh, till now, I talked about the model theory of modal logic. Now let's talk a little bit about its syntactic part or its proof theory. I have to define normal modal logic. By a normal modal logic, I mean a set of modal formulas that contains the following axiom schemas, which normal modal logic contains all instances of propositional tautologies, and also it has the axiom K, which is the distribution of box over the arrow, and also it's closed under these following rules. The first one is modus ponens, which we have in classical case 2 for propositional logic or first order logic. And we have another rule necessitation, which says that from if phi is valid, we can say that the box of phi is valid 2. The least normal modal logic is called the basic modal logic and is denoted by K. Let L be a normal modal logic. L proof is a finite sequence of formulas, each of which is an axiom or follows from one or more earlier items in the sequence by applying a rule of proof. A formula phi is L provable and denoted by this notion if it occurs as the least item of some L proof. I think you may be familiar with this notion, so I won't get any example, but if you need after the at the end of the course, I can give you an example. For some of our purpose, the basic modal logic is not enough because, for example, when we want to talk about the transitive frames or reflexive frames, as we say, there are some formulas which are valid in this class, but for example, P, then diamond of P is not provable in K. So we add it as an axiom to K and construct another normal modal logic, which we show that by KT, or for example, K4, which we add the 4 axiom, which is for transitivity to K, or S4, which we add T and 4 to K. KT, K4, and S4, we will talk about them during this course in the next sessions. The other concepts that we need to know is about soundness and completeness. A modal logic L is said to be sound and complete with respect to a class C of frames if for every formula phi we have phi is provable in L if and only phi is valid on C. Where define the validity on C, which means that phi is valid on every members of C. And there are important and known results in Kripke semantics. It is known that K is sound and complete with respect to the class of all Kripke frames. KT is sound and complete with respect to the class of reflexive frames. K4 is sound and complete with respect to the class of transitive frames. And S4 is sound and complete with respect to class of reflexive and transitive frames. There are some known results that we need them in the next sessions and we will use them. Another interesting property that we have in modal logic is the finite modal property. A finite modal property said that if a formula is satisfiable, then it's satisfiable in a finite model. Or in other words, we can say that a modal logic L has the finite modal property if there is a class C of finite frames such that for any formula phi, we have phi is provable in L if and only phi is valid on C. And it is known that K, KT, K4, and S4, all of them have the finite model property. I think it's enough to talk about cryptic semantics. Now we can stop this session